All right, here we go. So let's get to Bayesian. Oh, and then Sean, I'll fix that link for the regression. So thanks for the heads up on that. All right, so no presentations tonight. I'm not sure what to make from the 1-minute papers. I didn't look in the details sections, but it looks like need none going. So not not a lot of areas. Oh, I didn't.
Everyone is a data scientist.
Everybody's good on maximum likelihood. If not, ping me on Slack. I'm feeling a little punchy tonight. Sorry about that. It's a long couple of days. All right, so this is our last like new topic lecture. That I'm not going to have you do any homework or any homework or labs on this for a multitude of reasons. One is I imagine you're all probably working hard on your projects, so I'd like to let you keep focusing on that and catch up on any back work that you might have. The reason, and quite frankly, this is my lecture here on Bayesian is very, very basic, but my goal here is just to give you a little bit of a flavor of what Bayesian analysis is about. And also I find that talking about how Bayesians approach some of these kind of models and sort of their ideas will hopefully reinforce sort of the frequentist approach, right? And this notion of the central, so a lot of the inferences we make are really relying on the notion of the central limit theorem, that there exists some sampling distribution from which we can make those inferences. And Bayesians are going to kind of flip that a little bit on its head. So I'm starting actually at the top. If you, so the book that I put on the course website, by Danielle Navarro, she has a chapter which is I think a great supplemental book if you're looking for another point of view on a whole host of the topics we talked about this course. I think it's a fine resource, particularly that she makes it free, but she also has the last chapters on Bayesian analysis. So that's a nice place to start. But if you want to, if you really want to dig in, this is the book I recommend, John Kruski's book on doing Bayesian data analysis. I think it's the most accessible. So Stan was one of those things. So Jags and Stan both have interfaces from R to but there's sort of, as we're going to see, there's special languages to allow you to define some of these particular kinds of models. Now, if you Google around, you'll quickly find there are a lot of R packages to do Bayesian Bayesian models that are sort of counterparts. So, if you're doing something that would be a logistic regression, you want to do a Bayesian counterpart. There are packages to do that out there. So you can just swap it out. What's different is obviously how the models are estimated, but the input output can often be the same. Now, in my experience, a lot of times, logistic regression still used a lot, still performs quite well. But Bayesian classification models that are like logistic regression, or if you're just classifying more than two categories, tend to perform very, very well. Up there with like random forest, which is something you'll learn hopefully if you take either 622 or 624. Kruski has a whole bunch of videos. This takes you to his YouTube channel, some great stuff. A lot of what I'm doing tonight is really just a ripoff of Rasmus Spath. He has kind of this, I think they're each like 15 minutes or so. I'm going to use part one because I find his introduction, I think, kind of nice. Another thing, since coming summertime, you're looking for some nice reading. If you like history books, I highly, highly recommend this book, The Theory That Would Not Die. It's more of a history book. There is some little descriptions. It's about how Bayesian works. But it really kind of goes through because it's been around since I think Bayes wrote his first paper in the late 1800s. But sort of one of the more famous examples of using Bayesian analysis is Turing, cracking doing the Enigma machine to crack the German codes. He was using a Bayesian approach, but then it's been used a lot, like in industry or in the military and the like. And it's only really in the last couple of decades that academia has kind of started to push this. And the other piece that you might, if you're interested in this stuff, is you should absolutely be following Andrew Gelman's blog. He's at Columbia. He does a lot of Bayesian stuff. If you If you haven't already, I think I had a link in a previous slide deck. You should definitely join the New York City R users group. It's, I think, NY Hack Rs. If you Google that, you'll find it. It's on the meetup.com. Is where they post stuff. They have their own website. They do a fabulous conference every year. Last year's was virtual, which was still, it was a fantastic. I've gone to most of them. So Andrew Gelman's, let me see, I can probably, nope, wrong Andrew. Can't remember the name of it because it just comes in my stat modeling. Is this it? Yeah, here we go. I'll throw this in there for you. So yeah, Andrew Gelman speaks there. I think he spoke every year, but maybe one. Very entertaining guy. You can actually look up his talks from previous years. So these are sort of the resources that you should have available if you want to go forward. So to back up, we're going to start here, right? Which is, I think, how Bayes' theorem was first introduced, I think, in chapter 3, in the probability chapter. And the goal here is, what we're trying to estimate is the probability of A given B, where we know kind of the other pieces, right? We know B given A, we know probability of A and B, and we can, obviously, if we know probability of A, we can usually know the probability of its complement. And so I find it a little bit easier to understand if we work through an example. So here we got this 2x2 table that gives us information about number of women who have breast cancer and the positivity rate, right? So we have all this information if we look here. So if you have, a test positive, right, then 80% would have cancer, but 9.6 would not, right? Because we have 1% have cancer, 99% don't. But then we have this 80% of 80% of mammograms detect cancer when it's there, but 20% miss, and we have this 9.6 detect breast, that's sort of that false negative rate. And so then 90.4 have a positive rate. And so we know these bits of information, we can observe these. And so what we really want to know is, what's suppose you have a positive test result, what's the chances you actually have cancer, right? And there's a couple of ways you could look at it, right? So we know in this case, we're in this top row, and so if you're in that 1%, right? So it works out to be about 10.3% in that case, right? And this becomes useful when we want to get the probability of sort of of the accuracy of some test, right? So the chance of getting a real positive result is 0.08 or less than 1%. So the chance of getting any type of positive result is the chance of the true positive plus the chance of a false positive, right? And that's where we get that 10.3. But what we want to know is, what's the probability of having cancer given that an actual positive test, right? And so this is where we can substitute all these pieces in, and it's about 7.8% chance, because we have to take in account the fact that we have this sort of, we kind of have two columns, right? And we have the two rows, we have this 2x2 table. So we got to take into account all those bits. So it's not as simple. So if it all comes down to a chance of a true positive resulted by a chance of any possible result, we can actually simplify this formula, right, down to this. And this is, sort of the more general way that Bayes' theorem is kind of calculated, but it is derived from this full formula from all of the different components. So from a data point of view, because we're not going to solve problems, I mean, you can use Bayes and you will, but we want to move on to get to solving other types of models. And I like this slide by Chris Alban, right? And so there's these different components that go into the model. So we have, so what we want is some posterior distribution, right? So this is going to give us the probability of some event occurring, because we're going to collect lots of data. And so these are actually going to end up being distributions as we go through. And so we're going to have some prior, right? And often when you read about the controversy around Bayes analysis and what the criticisms are, it often involves this notion of a prior, where this is a distribution that you're coming, that is often should be or often based upon prior knowledge, and you're trying to leverage that, and it's going to go into the calculations. Now, I'm going to show where we can have what we call a naive prior, right, which is going to kind of equalize that. But Bayesians would say, well, if you have all this prior research, right, think about the frequentist approach. We do these null hypothesis tests, and we always go to the null, right? The null distribution is our starting point. And so the Bayesian would say, well, oftentimes you're not the first person doing this. You have some prior research, you have some prior data, you have some prior knowledge, and for this particular study, you're just going to ignore everything that happened prior or before this study, right? Anything prior, where if you have some sense of where it can be, you should leverage that, right? And so we'll look at through an example. I think that'll become a little bit more clear as to how that can be powerful, and how maybe that criticism sometimes is a little overstated, because oftentimes these methods are somewhat robust to even fairly egregious estimations or specifications of that prior distribution. Okay, then we have some likelihood, and this is often our data, right? The likelihood is, our data. So we're going to observe something, and the Bayesians can say, well, that's the truth. And so the way that this is going to work algorithmically is we're going to essentially simulate data given these different distributions, and observe how often we observe what we see. Okay, so let's go through an example. And like I said, this is adapted heavily from Rasmus Bath's workshop he gave in 2015 at a USARC conference. And I like this example because this is an extremely difficult problem to solve using a frequentist approach, but becomes somewhat trivial from a Bayesian point of view. And this goes to population estimates. And so as we go through this, you can also think, right? So the key why Turing was able to break the Enigma machine develop the Enigma machine to break the German code, was that he didn't try every combination, of the encryption keys. He could use prior information from prior runnings to create a subset of things to try, right? And so these approaches tend to be somewhat similar. So we want to estimate how many fish are in a pond. Not a large pond, so we're going to have some bounds here. We're going to have to decide what's reasonable. But what could we do? We could try to catch all the fish, but that's not practical or even possible. So we're going to devise this scheme whereby we're going to catch some fish, mark them, return them to the pond, let them kind of mix up, give it a little bit of time, and catch some more fish, and see how many in that second catch were caught, were recaught. In other words, did we catch any fish from the first batch the second time? So just presume I did this. I went out in a boat, I caught 20 fish, I marked them, I let them return to the pond, I let enough time go so that they could swim around and be anywhere in the pond. I catched another 20 fish, and 5 of them were marked, i.e. they were caught twice, right? So that's it. That's the information we have. And from this, we want to determine how many fish are in the pond. Okay, so what we're going to do is, so our strategy is we're going to define some prior distribution and draw lots of random samples from that prior to determine the probability of getting that. So what I want to do is say, I'm going to randomly, let's say, I'm going to randomly, draw a simulation where I'm going to randomly select 20 fish, shuffle it, and see how many I get marked again and the prior here is defining how many fish I think are in the pond. Okay. And so what I'm going to do here is what would be called a naive prior, because I'm going to use a uniform distribution. So I'm going to say, it's a small pond, so I have to put a cap on it somewhere. There can't possibly be more than 250 fish, and there has to be at least 20 because I caught 20, right? So, and I'm going to do this 100,000 times. And so I am, randomly sampling a number between 20 and 250, 100,000 times. Of course, I have to have replacement because 100,000 this is greater than the length of this. And you can see here's the first 10 elements, and this is what the plot looks like. So in essence, what I'm going to do in my algorithm is I'm going to say my prior saying, well, I'm going to assume there's 205 fish, and I'm going to run some algorithm where I catch 20 and then catch another 20 and see how many I get from 205. And then I'm going to randomly sample 20 from 130 and do this whole process, right? So the prior is really defining, you can think of it as defining what the initial guess for the number of fish in the pond are. So the next step is to define what's called a generative function or a generative model that's going to do fake data. So I'm defining this function called pick fish. It takes one parameter, which is the guess of how many fish are in the pond. Okay, so in the first one, it's going to be 205, and then it's going to be 130. So I'm going to call this function repeatedly, but we're going to start with 205. So if I call that, so I'm repeating 0 and 1, or I'm going to repeat 0, number of fish minus 20. So I have to subtract that 20 to get everything bound to 0. And then I'm going to have 20 once, right? So in this case, in the first case where I have, 205. So I'm going to have 185 zeros and then 20 ones, right? I caught 20 fish, I marked them. Then from this fish vector, right, I'm sampling another 20. And by summing that sample, that's basically saying how many fish did I catch a second time that was in the first one. Okay. And so I'm going to initialize a vector called n marked, and I'm going to do this 100,000 times. So I'm doing a simple for loop for each element of this n fish I had in the previous slide, right? So I started with 205. So in my 205, I got 0, right? 0 were sampled. But then I had 130. So with 130, I got 4. Okay. With 228, I got 1, right? 190, I got 2, if I lined that up correctly, all the way through. And if I look at the first 10, I never got 5, at least in the first 10. So that's the next step, right? Is I want to keep the ones where the n marked is equal to 5. Why 5? Because that's what I actually observed. When I went out in my boat, I marked 20, let them swim around, came back. In the second catching of 20, I caught 5. So I keep all of those, right? And so that's from n fish tells me, right? So that's that prior. So that tells me how many fish there were. And so if I plot it, right? So now this is what's called the posterior distribution. This is the distribution of the number of fish in the pond that resulted in my simulated marking scenario in getting 5 fish on the second catching, right? And so I could just take the median. So it's skewed. So I might take the median. So my guess might be to say there's about 100 fish in this pond. And here I put a 50% confidence range on it. And so I might say I'm 50% sure there's somewhere between, it's a little less than 75 and 130 fish in this pond, right? So that's my posterior distribution. So now we tend to call it confidence range instead of confidence interval, but my confidence is not going to be derived from this notion of a sampling distribution that I actually never see, right? We're not calculating standard errors or anything like that based upon that. We're actually going to we actually have a distribution we can look at, and that we can read our confidence and our estimates off of this distribution. Okay. Now let's suppose I have, some fisherman comes and, is a supposed expert in this. And this expert says, you know what? I believe there are 200 fish in this pond. So instead of defining a uniform distribution as my prior, I can do some kind of, binomial distribution, right? So here I do a binomial distribution centered around a 200. And so, this is going to be my prior distribution. Everything else is going to be the same, right? So this n fish, right, each element in that vector is going to run through my generative function. But what's going to happen is I'm going to guess, 200 way more than I guess 400, more than I guess 100, right? So it's the number of times that's going to occur. So I run that through, and so here's the posterior distribution from that. So my overall, the median estimate is a little bit larger. 200 is clearly not in my interval, right? It seems very unlikely that 200 is it. So even in this case, that my so-called expert is wrong by quite a bit. The model still did fairly well in capturing where that true estimate is. Okay. Hold on one second here. All right. So give me. I got to do one thing. I'm going to start up this Shiny app that I should have started up before. So you got to bear with me for 1 second. Let's see here. Sorry about that. I should have had this up ahead of time. I need to copy this. Oh boy, why is that not loading? Oh no, I screwed up my R environment. Let me see if this will work. Give me 20 seconds, I think. Oh, this will be unfortunate if this does not work. Here we go. Yay. I just got to open it here. Okay. Sorry about that. My apologies. All right. So I'm going to show this little Shiny app in just a second, but let me set this up. So this is, I think this is actually one of Bayes' first problems that he wrote about. Now, of course, at this time, most statisticians would write about games, and they would often, invent these games to talk about probabilities. And so it's often called Bayes billiards balls. And so sort of the idea here is, assume we have a pool table, and we're going to define the length of the pool table as 1. Right? So we're just going to say it has length 1. So it becomes convenient for some arithmetic. I'm going to throw an 8-ball on the table, and it can land anywhere on the table, right? I'm going to presume it's, level or what have you. But I'm not going to tell you where the 8-ball is. All I'm going to do is throw subsequent balls, and I'm going to tell you whether or not it landed to the left or to the right of the 8-ball. That is the only information you're going to get. And from that, you have to tell me where the 8-ball is. Right. So this is kind of one of the problems he talked about. So in this, I wrote this little Shiny app to kind of simulate this. So I'm going to start with a prior distribution, a quote unquote naive, right, Bayes, because I'm going to assume the 8-ball is anywhere on the table. There is this option here to show a histogram, just to satisfy. I do this to satisfy myself that it is uniform. We see some bumps that, I could change the bin width. The problem with density plots is when you have kind of a hard edge or ceiling or floor, the density kind of tails off, but it is indeed uniform. Okay, just to say that up front as an aside. So this is going to be my initial set of guesses, right? In the first throw, right, I see that the first ball landed to the left of the 8-ball, right? So I'm going to keep track of it in this table. So what I'm going to do is for all of the values that are, from this prior distribution. So I'm going to go, so one way to think about the way the generative function works here is when I get to 0.5, I'm going to say, okay, if the 8-ball's at the midpoint, right, I'm going to randomly draw a number between 0 and 1. And if I draw a number smaller than 0.5, I'm going to throw it away because I'm trying to get that would be wrong. And if it's to the right, I'm going to, no, if it's to the left, I'm going to keep it, right? And if it's to the right, I'm going to throw it away, right? And so I do that through all these values, and this is what I get from all of those random, generations. So like intuitively, right? If I say the ball landed to the left of the 8-ball, right? Hopefully you're thinking intuitively, well, that means it's probably more likely to the right side, the 8-ball's to the right side of the table. Okay. Great. Right. And so I plot that here. So right now, my best guess is, it's probably somewhere around this 0.7 mark. This is a 50%. You can change it, confidence range. And so, you look at the distribution, the mean of the distribution. Okay. Let's say we have another ball. Okay. The second ball also lands to the left. All right. So first thing I'm going to do is I'm going to take my posterior from the first iteration. That's going to be my prior. I'm not going to start from scratch. I didn't move the 8-ball, right? So I already have some evidence that the 8-ball is to the right side of the table. So I'm going to use this and I'm going to run it through that generative function, and I end up with this posterior, right? So you could see now I'm guessing, maybe it's over, at the 0.7 mark, the 50% confidence range shrunk a little bit. So I can do another. Okay, so now the third ball lands to the right. But what I'm going to do is take the posterior from iteration 2, becomes the prior in iteration 3, I run that through. And so, I shifted a little bit to the left. And let's just maybe do 2 more. So now it landed to the left, and now it landed to the left again, right? So I've only done 5 iterations, and this is kind of where I think the 8-ball is. And we could satisfy ourselves and say, well, let's actually look at the pool table. Oh, well, it turns out, sometimes you win them, sometimes you lose them. After 5 iterations, I didn't quite capture it, right? It was actually at the 0.55 mark. Often you don't have so few. And if we do a few more, if we even get to 10, right, it's going to start to, stabilize. So, how does this translate to, when we think about our regression models and the way we've estimated, sort of the parameters is all so far this semester has been based upon this notion that there exists some sampling distribution. We observe data, we estimate sort of means and standard deviations or variances. And from that, the notion that we believe that the sampling distribution is normal, we can read that off. What the Bayesian is going to do is say, all I know is my data is real, right? So we observe this. So I'm going to simulate data and see how often I get what I actually observe. And that distribution is going to define where I define my likelihood or probabilities of my outcome. And so there are kind of drop-in counterparts for a lot of those things, but the way the models are going to be estimated are going to be obviously very much different. I think one of the reasons why Bayesian analysis is just now in the last, really even the last decade, maybe 2 decades, become much more popular and relevant is that, as you can see, this is a fairly computationally intensive procedure. And so as, Moore's law has played out and computers have gotten much faster, makes these kinds of methods much more accessible and usable, right? We can easily run these. I can run fairly big Bayes models on my laptop without too much trouble. Definitely take longer than maximum likelihood estimations, but so that's kind of where we are. So hopefully this just gives you a flavor, right, of kind of how Bayesian analysis works. Happy to take questions. Again, sort of my goal is twofold: not to make you Bayesians, because I'm not sure I'm even there. I'm sort of a pragmatist. I will use whichever method is the most appropriate or most accurate in any given situation. But it's nice. This is a nice thing to have in your tool belt, and probably something you'll encounter much more as you get a little bit deeper into the program. Daniel.
I have a quick question.
Yeah.
So I'm trying to think through the billiards situation where instead of getting information about the balls one at a time and updating, you are simply told, I threw, how many are up there? 10? I threw 10 and 6 landed to the left and 4 landed to the right. It seems like you would get the same confidence interval, but you would not be going through this like distribution updating process. Is that?
That is true. Yeah. If you knew you were going to get 10 at a time, then I would write my generative function in that way, that I would sample, you know, 10 random numbers at once and look at the proportions, you know, left to right to define that posterior distribution. So by describing it this way, or setting it up this way, and this is the way I think Bayes, it's been a couple of years since I read the original paper. I think I even linked it. Did I link it here? Well, there's a little bit more description in the about. So you can actually go, I think, read the original essay from 1763. He talked about it that way to reinforce this notion of the prior, right? That you can kind of update as you get more information, right? And if you look at the ways that it's, you know, if you look at, let's go to Turing again, right? If you know, he knew that the Germans were changing the encryption code every day, but he kind of had some information from other intercepts about the range that it could do, and also what they solved in the previous day, right? So in that case, where you have a rolling, you know, input of data, right? That's the way you could do it. But I wouldn't necessarily, if I knew I was always going to do 10 at a time, I would write my generative function to do it that way. So you're right, Daniel. And that's why things like Stan, I think, is sort of the work out of Columbia, and JAGS is another popular. Those are really languages specific for Bayesian, and the reason why they have their specific language is you have to define these generative functions to do this in these kind of contexts. Now, if you just want to do regression, like I said, there are packages that kind of implement that for you. You can just do it where I'm just trying to predict some outcome, like in predictive modeling or machine learning cases. You know, but if you're trying to solve problems like this, they're all unique, right? In such a way that you got to define that generative function. And that's what those languages are designed for. So did I answer your question? I think I did, right? So if I knew I was getting 10 at a time, I would do it that way.
Yeah, that I understand. I mean, that definitely makes sense and answers the question. I guess I was just phrasing it slightly differently, not so much that we're doing 10 at a time, but that you just one time get information about 10 throws and then you're done. But it doesn't really matter because.
Yeah. Well, it depends on the context, right? Would you get another 10? You know, that's the question. Like, or is it one and done? If it's one and done, yeah, I would code it up that way. So that'd be an interesting exercise. I don't think I could do it off the top of my head quickly. Writing these generative functions usually takes a little bit of thought, but
I have a question,
yeah,
that's a little
but that
bit
would be
more
neat to look at. Go ahead.
Oh yeah, I was saying I have a question that's a little bit more specific to this problem. Given how you framed it, is there a minimum number of iterations where you would have a certain confidence as to where the 8-ball is located?
No, well, not really. If you notice, it's not it. So this is where things get different, right? So in the frequentist approach, as n goes to infinity, right, the standard error shrinks, right?
Yeah, that's my thought.
Because we have n in the denominator. Note here, we got at the 6th iteration here. Let's look at it, because that's why I have the table. So we're going from 0.8 to point. Is that right? Is this iteration 6? Oh, I'm sorry. I need to. That's the median. Okay, so we're going from 0.66 to 0.86. So our 50% confidence range is 0.2, right? But then in iteration 7, right, we got something going in the different direction. And notice that the 50% confidence range increased. Now we're at 24, right? So we are are essentially our N increased, but our confidence range increased instead of decreased. So, so the answer is, I think the answer to your question is no, right? There's not, the more you have, the better off you're going to be, right? And you're going to see this less and less as we get, it'll probably stabilize to where it's just shrinking. And we're dealing with a smaller, right? Which is kind of what Gossett was trying to do with the t-test, right? To account for, each additional observation is going to have a larger contribution to the variance estimate. I don't know if there's a good rule of thumb here.
Well,
But
not a specific number. I'm thinking more of convergence, that as you increase N, that, I mean, because there's only so many places the 8-ball could be. And
Yeah.
as you know, left and right is kind of like a binary searching it.
Yep. I think as N increases, it is certainly going to stabilize. But these are often, sometimes in this case, they're trying to be used in small number of observations, right? So the frequentist, right, the textbook's going to say, well, we need at least 30 throws before we can really invoke the central limit theorem, right? And here we're getting pretty darn close after 10. But again, right, the confidence interval or confidence range is not from the central limit theorem. It is literally from this posterior distribution, right? From the results of our simulation. We actually have a distribution that we can draw it from. So this notion of minimum sample size that we have in the frequentist approach doesn't really carry over here.
Okay.
Other questions? Well, if there are no other questions.
So,
go ahead.
Was one quick question?
Yeah.
So, which theorem would you suggest? Like, will it be a central theorem which you have to apply, or it all depends on the problem we are trying to solve?
Oh, so for predictive modeling approaches, sort of the way, and I only kind of alluded to it last week, and I think I just mentioned in passing this notion of like doing n-fold validation. I think what I showed last week is we randomly selected 70% to train, and we validated with the other 30. So in practice, what we do is we do that, but then we do within that 70%, we do n-fold validation, and briefly what n-fold validation, typically 10-fold, right? You're going to randomly divide the data into 10 groups, and then you're going to train a model at 90% and validate with 10%, then validate, and then you're going to go through, so you're basically going to train 10 models and validate 10 models with that holdout set. And then you average the accuracy across those 10 models. So that's kind of how n-fold validation. It's n because you don't have to do 10, you could do 5, you could do 20, depending on your sample size, but 10 is commonly what's done. And so that gives you sort of, as you're going, so I'm going to do that, say, with logistic regression. Then I'm going to do 10-fold validation with a random forest methods. Then I'm going to do 10-fold validation with a Bayesian model, right? And so now I have like 3 different approaches, and now I have 3 different, accuracy estimates. Then I'm going to pick the one that has the best accuracy from that 10-fold validation approach, and then actually validate it against that holdout, that 30% that I randomly selected and set aside somewhere else. So in practice, that's what we do. We try a whole bunch of different approaches because different models will behave better or worse given different data. So there's not like, it's often, there's problems like this where obviously the Bayesian approach is going to be the best, right? Frequentist approach this is going to be a hard problem to solve. But because of the way the generative functions are, some of the assumptions that we have under the frequentist approach are kind of relaxed. Like we're not presuming normal residuals, right? That whole notion that the residuals there is not there, because we're kind of have this generative function in kind of simulating data to estimate some kind of posterior distribution. So if conditions are met, sometimes logistic regression will outperform Bayesian methods, and sometimes not. So no, Richard, no, it actually doesn't work out that way. So Richard is asking, wouldn't the average from the n folds be the same as training on the entire data set? And the reason why is right, because you're only training on 90% and validating on that other 10 and then kind of cycling through. And there's a number of advantages, but the one way to think about it is if you had like one outlier, then one of that outlier is only going to, well, I guess that outlier would be present in 9 of the 10 and not in the other. Yeah, it doesn't work out that way. For a host of reasons. I'm just having a difficulty articulating right at this moment. If you train, the problem when you train and validate on the same data set is you tend to overfit, right? And you don't want to validate against the same holdout data set across everything, because of the random process, you could, again, you could end up going a little bit astray. So I'm going to think about that, Richard, and I might come back. I might post something tomorrow. I think I could devise a little simulation to show why that is, particularly if you have a non-normal distribution. If you had a normal distribution, so the n folds is not with replacement. So you're literally, there is no replacement. So you're assigning a number 1 to 10 to each observation in your data set. And so they will be in the validation set 1 out of 10 times, and 9 out of 10 times they would be included. So it's a little bit different than bootstrapping. So if you had replacement, then that would essentially be a bootstrap. That's a good question, though. Yeah, the replacement would obviously make it different.
I have a question about the fish in the pond that just maybe might help me understand better the Bayesian thing. It seems like if you just use the frequentist approach and a little math, you're always going to come up with the best estimate. Maybe you would call that like the maximum likelihood estimate. But maybe from the Bayes, you're getting like a better idea of what the distribution might be. I'm not sure if that's true or not, but it seems like from the fish thing, you would never have a better guess than that there were 80 fish in the pond, because a quarter of the fish that you pulled supposedly randomly were marked. And so
no, you don't know that. This is all we know at the outset.
Right. So you got a quarter of the 20 that you caught were marked afterwards, right?
Yeah. Oh, I see what you're saying. So,
yeah, so you figure 25% of the fish in the pond are marked, and you marked 20, so there should be 80 in there. And obviously I just don't see how you would ever come up with a better guess than that, as far as like the maximum, guessing your mean estimate or whatever it might be. But I can see how like the Bayes might give you a better idea of distributions. I don't know.
Because I think the Bayesians would estimate closer to 100. That's an interesting, I never thought about it that way. If you got 20%, is that, I'm not sure that would be the frequentist approach, but that's interesting. So you would have gone, yeah. Your arithmetic is sound, but is that, so what would be the standard error? How would you calculate a standard error from that?
Right, exactly. I have no idea.
I don't know. In fact, students tend to ask me this, and you're kind of alluding to this. I actually don't know how to solve this problem from a frequentist approach.
Well, the interesting thing you said about how the computing power has helped the Bayesian come back into popularity,
Mhm.
it seems like it could have just as easily just driven a wedge further between frequentists and Bayesians because, you know, you can simulate all these things 10 million times and get a much better answer than probably any possible math would give you, I think.
It
You know,
seems that
roll the
way.
pool, just roll the pool ball 10 million times and I can tell you exactly where it is on the table. You
Yep.
know,
Yeah.
there's just no way it's going to be any different.
Yep. Yeah. So you have a limited number of observations, but you know,
Yeah.
theoretical infinite amount of computing power, right? That's kind of where we're at. Yeah, I think you're right. And the debate has died down. I think at least in the circles I follow, we are. If you're an applied data scientist or even an applied statistician, you know, you're going to use whatever works the best. Now, interestingly, Bayesian hasn't really caught on a whole lot in the social sciences. I don't like in the psychology or educational literature. I don't see a lot of people using it yet. Just a little bit here and there. Some of the sort of methods journals are starting to publish some stuff, but yeah, in epidemiology and obviously anything machine learning related, it's catching on because it's a remarkably useful tool. And if you run it, right, so if you use some of the Bayesian packages, there are like, so I can't remember the name off the top of my head. So I could say Bayesian logistic regression. Actually, I can even do NR. Was this the one? You know, we can pick one of these. I'll probably recognize. Oh yeah, well, there's Bayes plots. Anyways, so you run these. So this one's using, okay, right. This is using STAM, which is, you know, it even calls it GLM, right? As if it's a generalized linear model. And, you know, you specify these things. Oh, well, this one's actually doing, logistic regression. Where's the Bayesian, right? The outputs are going to often look the same. So trying to find where they still doing a lot of, maybe that's a bad one. I don't know that one. But you're still going to get parameter estimates in the same way. And you generally specify the models in very similar ways. So, you know, it becomes fairly useful. So, yeah, so here we're looking at, so this did a log of it. Well, can't find the R code. It's, you know, a lot of this is in the, well, you can either go to some of the references I have on the website, or, you know, that Kresge book, or in the Navarro book will show how to actually specify those models. Other questions? So real quick on, so which one was that? Sean, it was the multiple regression slide. Is that the one that was broken? Yeah, okay, I'll fix that right after. So looking at the schedule, just a couple little housekeeping things. So we'll do a final meetup next week. Just be a lot of housekeeping stuff. I'll introduce the final exam. Usually the final exam starts after the final meetup, but the way reading day fell this week, the final exam will be made available on the 19th. Although who would, okay, right, because we presentations are this week, so that'll be fine. So yeah, so yeah, we'll be doing those soon. So next week will be our last one. If there's some burning reason to meet on the 19th. Oh, actually, I can't do the 19th, right? Because we're that's right. The 19th is our graduation for students who are graduating the program. Since that evening. So what will be the format of our final exam? I haven't finished quite yet writing it. It's typically about 10 or so multiple choice, a couple of short answers, and then I give you a little data set. Think of it as like a mini lab to do some analysis, and then there's a series of questions that you can answer about the data. It is open book. I just ask you to work alone, don't collaborate. It shouldn't take more than an hour or two to complete. Assuming you've done everything through, you shouldn't be looking up a ton of stuff, but if you need to, I'm not a big fan of memorization. So I want to know that you can apply what you learned. And if you've been coming to all the meetups, the questions probably shouldn't be a big surprise. I kind of emphasize in the lectures what I think is important. So, technical stuff, I'll post in Blackboard so it'll become available. I'll make a note in the Slack, at the same time. I'll post a PDF with all the questions, and then I'll give you an R Markdown file. The data set is small enough that I just embed it in the R Markdown file. So there's no figuring out how to try to load data or anything like that. No, I mean, only that it has to be done by midnight on the 23rd, because I think I need to submit grades not too long after then.
Jason, one other question along these lines.
Yeah.
When we started out, you were able to provide us, I think, up to homework 3 with some answer sets so that we could check whether, we were on track or not. Are you
Sure.
going to be able to make that available for the remainder?
Yeah, I'll do that. I'll do that tomorrow. My apologies.
Great. Thanks so much.
Yep, not a problem. All right. Any other questions?
Excuse me. I thought
Yeah.
I'd mention again, I sent that link actually not too long after we talked at the beginning of class. When we
Oh.
talked, you mentioned that blog. That wasn't very useful, but this is one they sent earlier. That
Oh.
actually explains everything that I was showing you, and I actually think is exactly what you need to get started.
Okay, thank you. Yeah, this is not the blog post I saw. When was this published? Oh, in October. Okay. Okay, cool. Thank you.
Yeah, no
Thank you,
problem.
Zachary. Yeah, I'll give that a look.
One thing I should mention,
But this looks
it's-
like it's specifically for like the desktop version.
yeah, exactly. I don't know anything about the browser version / the, I don't even know what it's called again. I'm sorry.
RStudio server, not a big deal.
RStudio
But
server, yeah. I don't know exactly if they've added that integration to the RStudio server version yet.
I've read that they have. What took me a while to figure out, because they talk about it in terms of they're kind of shifting a little bit. So it's RStudio Connect. So I discovered that after, because I was actually Googling for RStudio server
Oh,
Python, but then I just happened to stumble from a Stack Overflow that linked to it, that the article was like using Python with RStudio Connect. Connect, I think they're trying to uniform their server products in some way.
One thing I should mention, I'm blanking off the top of my head, but there's a specific command to access Python from within R, and then R, the other way around, I should say. You can, like I said, access anything you create in Python within R, and you have to use, what is that? I'm just trying to go back. Okay.
Yeah, I think you can do it. There's a reticulate.
No, it's not even that. It's quite literally within R, trying to access anything Python. It's this command right here, pi, and then just a $ sign. Yeah.
Really? So if I
And-
do pi, of course this is not working. Give me a command. Like what's like something simple?
Well, you can just create something in Python, like say x = 1. Quite literally just that.
Like this?
Yeah. If you create a Python
Although
chunk.
it just created an R object because Python's not working. So cool. But that's, you know what,
Oh,
actually,
sorry,
if I was
that's
looking,
if you that's if you already have it already created. I should mention.
because I
And
was
you don't-
doing it where was my little, I had a TensorFlow. It was like TF $. So that must be how it works. And it's not in this R script. It's in another RStudio. Let's see. Oh no, I'm in a different project. So never mind. I can't find it. I do my thing. I see 3 different RStudio windows right now. So I'm, but thank you. I
Yeah, no
will,
problem.
this is, oh, damn it. When I do that, cool. So I'll read this over. So
Yeah,
what
I
do you
was-
use? Do you just use the full Anaconda or do you use the mini Conda?
Right now, I'm just using default Python 3.85. I myself, like, I've not really messed around with Conda. I've heard mixed things about it.
Okay.
I've heard it can get really easily corrupted and leads to ruin.
Yeah,
So-
Anaconda has a bit of a learning curve to it. Like, I only use Anaconda, but
Okay.
when you start off, if you don't know what you're doing, you can really mess things up.
Maybe you can answer this other question. So if I go to, well, let's just say, let me see if I just go to my home directory.
Can you just
And,
type Conda?
No, it doesn't work.
Okay.
Because some things were wanting to do this. So if I go to here, yeah, it's CD Python. So whenever I install these, so if I go to the bin, there's always, and in the default, like when I set up Ubuntu by default, right? So there's Python, and then I have to, oh, but this one doesn't even have, but there's always a Python, there usually is a Python 3, but
I think you can type in your computer in that terminal right there, which, and then Python.
yeah, it's going to give me the 3 right now because I think I may have created a symlink to it. And so if I do Python,
Right, but even that Python, I don't think is the correct one because the one you want is the one inside of the environment, right? The one inside of Miniconda.
which is not here. I can't remember where it got installed.
Right.
Type where is Conda.
Just like this, where is?
Yeah, I mean it's a Linux command, so huh? What?
Okay. At least you're making me feel a little bit better that I'm not absolutely going.
I would have preferred an
Crazy.
error message than that.
What I can tell you for certain is it should
Yeah, look
work
at
on
there
your
should be-
desktop version now.
Okay. So if I go to .conda, so what's in here? So there's
Yeah,
the,
go ENVS.
yeah, there's the.
Yeah, so that's your
articulate-
environment.
Okay. Conda meta. Does that make sense? I don't
Well,
know.
I mean, you have to go that far, but doesn't the command conda activate and then r dash reticulate?
Yeah,
Can
it
you just
says
type that
not
command?
found. Yeah, it's conda what?
Activate, although the conda command is not found. Okay.
Yeah, so conda,
And-
yeah. So
Why
where
would the
would conda be in, is it just not on my path? Would it be in the, is that included with Python or no, that would be in mini conda and I.
No, conda is a system level command.
Oh,
So your terminal here has to know where to find that. Like on Ubuntu, that would be in your bash RC file.
okay.
I don't know what they call it in Mac.
Well, this is Ubuntu right now because I'm in our studio server.
So to type VI and then the squiggly line / dot bash RC. Yeah, go to the very bottom. Or just search the word conda.
My VI is weak. What's the, I would do, what's this?
Just
Search
/
conda.
Oh no, but you have the colon there. Just type / conda. Yeah, so okay, so your conda path is not in there. That's why.
Okay. All right.
And I think you know your conda path because that was the one in your home directory, the .conda.
Yeah. So that would just be this? Or do I have to point
no,
further
that-
down?
No, I think you want the one that would be. Actually, maybe that is the one.
Well, the problem is this just for me? The other piece I'm trying to do is install this globally.
Well,
So-
this will just give bash the instructions on when you type the conda command where to actually activate the environment. And then
Okay.
RStudios will then take it from there. Every time you run a Python script, it'll know which Python to run from.
I see. All right.
Right
So
now,
the
I
other
think your
thing
problem is
I
that-
should
yeah.
do is, I guess, on Zachary's, if I update RStudio, I should be able to just do it from the dialog box, right?
I think, what was it? Prior to the latest version of RStudio, you were able to use Articulate like within R chunks. Kind of similar to how SQL, I forgot what it was. There's like an SQL package where you can
Yeah.
yeah, SQL within R itself.
Mhm.
But now I guess the introduction of doing it this way is that you can just create Python chunks just by themselves, and actually they just work without having to do any setup once it's being pointed in the right direction.
Yeah. Yeah, I'm looking forward to that because I do want to learn Python and more. But I find the notebook metaphor not conducive to how I work. I like IDEs. I like having, consoles and script, So if I could use RStudio to just code Python, that would be, because you can just create just .py files, right? And it'll work like an R script.
Yeah, I think so. I
I think
definitely
the command I posted there should be what would work from you. The only problem is I didn't see a bin directory in your conda.
Yeah, I noticed that
directory.
before. So,
But this is
Alright.
pretty much how you would append the path.
well,
I
luckily
honestly-
the chat will save when I close.
sorry, but
Yeah.
I honestly find it so fascinating that difference in opinion people have between liking it in console versus in the markdown fashion. I kind of got used to early on how it looks like when you have different chunks, and I prefer that so much more now. I feel like it's so much more unruly when you have it just like free floating with nothing separating the code you have.
Yeah, I'm been doing this too long another way. And my, in the late 90s and early 2000s, I was a Java programmer largely. So that, coming from, I used IntelliJ a lot, and just that way of working, just where then it wasn't even interactive in the way that R and Python are. But I guess, I don't know. Some people like it. I like, I want that stuff out of the way when I'm writing around, I guess. I don't know. And it's a lot of scrolling.
Another one is PyCharm. Folks has been using a lot. PyCharm IDE.
Mhm. Which is it?
I have my workplace.
Yeah,
I've been-
PyCharm.
Yeah,
PyChar. I don't know that one. I just
You can think
downloaded
of PyCharm
Spider.
like the RStudios of Python.
Because I'm honestly not sure. Sorry, this goes back to
PyCharm.
what we're talking about, and it's completely different from PyCharm. I'm not sure if you can do.
Oh, it's by JetBrains. So they're one of the original like Java IDE people. Neat.
Yeah, the
Okay, I'm
company
sorry.
JetBrains built a lot of IDEs.
All right, neat. I'll give this a whirl. Did you use PyCharm or do you just use?
We use PyCharm as well as Jupyter Notebook. Like different kind of flavors. There are people who don't like IDE.
Personal preference. I get it. It's like, yeah, it's just me. And I
but
can get
sometimes you
over it.
don't always have a choice. Like
Yeah.
for me, what I do at my job, I'm moving from server to server all the time. So I exclusively type in Vim because that's the only thing that's available in every server.
Wow.
Oh, once you are hooked up with Vim, you are done. You don't want to
Yes.
come back.
Never.
Even locally now, I don't use any IDEs. Like RStudio is the first IDE I've used in like 3 years.
Now, I do believe you can. RStudio supports Vim bindings.
Oh, well, I'll look into that. But I mean, like I just use Vim in the terminal. That's pretty much
Yep.
where all the coding happens.
Right. But if you want to navigate the source code, I thought you could do it.
You can still do it with Vim in the terminal.
No, I know, but no, not just in the terminal, but like in the source editor. Maybe I'm wrong.
Oh, you're talking about on RStudios?
Yeah.
I think you could because you do have a terminal tab at the bottom there. Red console and then terminal.
Yeah, I'm trying to. maybe I'm totally missing that. Vim. Says RStudio's code editor includes a set of lightweight Vim key bindings. So it's in tools, global options, code editing. Tools, global options, code editing.
Oh, Professor, we don't have the 1 minute paper today.
Oh, yeah, don't worry. I thought I put it in the chat a while ago, but maybe not. I'm not worried about it.
Oh,
No, you did already.
Okay.
I see this one forms link, but this doesn't work for me. Oh, you forgot the
Oh, there it
H.
is. Key bindings. Yeah, so you could use Vim, Emacs, or Sublime Text. So you can use your search, your navigation, and stuff like that. Here, I think, let me see. Maybe I'm talking about something different, but like right here, there's Vim.
Oh,
And
but
if I-
what does that do when you select Vim there?
So I think, well, let's try it. So I don't know if I want to do this. So if I do,
What's red now?
yeah, look at, yeah, so I type // now I can type,
Oh, I see the.
I
Oh,
can
very
do,
interesting.
I could do colon, and now I can, I guess if I do W, will that close it?
That-
No, I don't know.
No,
what
that just saved.
Oh, right, no, it's
W
quit.
is for right.
Also,
Yeah,
did you
look
know,
at that.
Did you know,
Quit.
Professor? Oh my God.
So there you go. So you could just be in the IDE and use your Vim. I give you a lot of credit for learning all those, by the way. I
By
learned
the way,
just enough.
Professor,
Yeah.
tangential, but did you know there's actually a keyboard shortcut for automatically doing the pipe?
Oh, I did, but it's what is it?
Control Shift and then M.
Yeah, that right. Yeah, cool. Now, what's going to happen in R4.1?
I wonder. What are they
With-
changing?
R is going to have its our core will have its own pipe.
Oh,
It's vertical, the pipe character greater than. So it's actually going to only be 2 characters.
simpler. They might still just use that command, but it's just going to be easier to type it. So you might forget about that and not even need to worry about it.
Yeah. So I have to decide between now and the fall, do I change my well, I guess it's Magritte pipes to base pipes. There's a debate going on Twitter. I don't know what to do.
Don't pick a side. You're just going to get destroyed either way.
Oh,
can't,
well, I got to tell you how many times I go to run just something simple like what convinced me on the pipe is going from the table function to the prop.table function. To just do that as a pipe is so slick. So I can't tell you how many times I do that, and then I go, oh right, I didn't load the Magritte or Tidyverse package yet, and I got to go do that. Where if it was just there, it would just work.
Yeah, it's not. I don't think about that because I'm so used to loading Tidyverse first thing. It's always
Yeah.
such a default thing I do. I never have that issue.
Me too, generally speaking, but it happens to me every couple of days though.
Like it would almost seem like at this point they just have the Tidyverse become part of base R.
Yes, I
Oh.
agree. Same thing with Python with the package pandas. That was the first line I type in.
Yeah. So yeah, I think that relationship is getting better.
Oh, it was a bad relationship.
No, well, I think there were some, oh, I don't know how to say this. I think there were some R core people who were not happy with how RStudio was kind of taking over what they thought were some core functions. And I don't know if this is exactly the fault. This sort of now we're kind of in rumor mill, but RStudio has wanted to package R into the IDE. The fact that you have to install R separately and then install RStudio, or RStudio can't just go get it. It's in part a licensing problem. It's because of the GPL that sort of seems to preclude RStudio from doing that. But there seem to be other projects that get around it, but I
Right.
think it's softened because in the last several like major point updates, I mean, RStudio is contributing a lot to the R core. Some of it is performance. A lot of it is debugging hooks. Like RStudio is making a lot of contributions so that when you get an error in RStudio, you actually get a proper trace back that you can click and get to the error more easily. And quite honestly, it may have just been one person on the R core team who is not really active anymore. I think he may have finally retired. In fact, when I was doing a lot more CRAN submissions, it was always like crossing your fingers that you don't get him to review your package because he was just mean and not polite. If you screwed something up, and it's easy to screw something up on a CRAN submission, it's rarely do you get it on the first shot. But lately, when I submit stuff, they are not, if you have a problem, it's not like, you don't just get an error message. You often get like, oh, you should try this, or this is missing. They actually point you in the direction of what to fix. Like I had a package rejected because I didn't use the proper capitalization in a function title. It's like, really?
All nitty gritty things like that. That's ridiculous.
Yeah.
Very
But CRAN is such a beautiful thing. I mean, that's why I think R became so popular.
What blows my mind though, and this is something I had to deal with recently, when you want to update your R version, that you have to use a package within R itself if you want to keep all your old libraries the same way. You can't do it for like, there's no base way of doing it. It will delete everything you have.
Well, it doesn't really delete it. I think it just changes where the library path is. So,
right.
So you can specify that in your R profile where the libs is, but I tend to not recommend that anymore.
There is another way you could do it, at least on Ubuntu, because I had R 3.3 before we started this class, and I had to update it to 4.0. But it went smoothly. It was just very hard to find the commands.
But like I said, there's a library dedicated to doing that, and it makes it so easy.
Yeah.
But it's just crazy to me that it's not something that's part of base R itself.
Yeah, maybe someday. Yeah, I don't know what to. So now, I used to, in all my R scripts, have the install that packages command like at the top, sometimes commented out. But nowadays, RStudio, if I load an R script, it looks at all the library commands, and if the package isn't there, it gives you a little like, do you want me to install this for you? And what's even nice is it does it in the background. It doesn't block the console anymore. That you now have that jobs tab. So it's making me lazy.
I think that's the direction of just coding in general. There's gonna be a lot more tasks that are automated. A lot of things that were tedious and just pains in the butt, they're now gonna be something you can just have done automatically for you.
Yeah. Well, I've been looking into on the DAX project, looking at the framework. So I haven't touched a piece of Java code in 15 years. And I remember I had to code my own model viewer controller framework. And now with like Node.js and all that stuff they're using, it's like, oh my God, like.
Oh yeah, I know with Android, especially an MVP is like something you just import now.
Yeah. It's like I had to code that myself.
Framework.
Yeah. All right, gentlemen. And yeah, I think it's only gentlemen. All right, we'll see you soon.
All right.
Oh, Daniel, holy crap,
Hey.
you had a question. So let me stop recording.